Hello everyone, welcome to the lecture series on Foundations of Deep Learning Concepts and Applications. So, we had started with the autoencoders, and in the previous session we have seen the types of autoencoders. We have understood its architecture, and we have also seen the code level understanding. We have seen how to implement shallow autoencoders, deep autoencoders, CNN based and denoising. These were the topics that we have discussed in the previous session, and in today's session we will first look into the limitations of autoencoders, and then we will start with variational autoencoders. Under variational autoencoders we will see the architecture and then the loss function. So, we will first look into the limitations. So, before we start before we look into what are the different limitations of autoencoders, let us quickly understand the architecture once again. So, we will have an input. The input is passed to an encoder, which we have seen in the previous session, and towards the end of the encoder what we are obtaining is the latent space. So, this is what we are going to obtain towards the end. Now, whatever is the latent representation that we have obtained, this latent representation is a compressed version of an input. It is a compressed representation, which means the size of the latent space is much lesser comparing to an input. Now, this latent representation is then passed to an decoder. Now, why is that we have to pass it to the decoder? Because if the first objective is to learn the latent representation, the second objective here is a reconstruction. So, how do we reconstruct? Decoder is responsible for reconstruction, and for decoder, what is the input that is passed? The latent space is passed as an input to the decoder. So, decoder will reconstruct and then we get the input back. So, this is although it is an output, but whatever is the what output we get is the reconstructed version of our input only. So, this is what is the overall working mechanism of autoencoder, where the first objective is a latent representation. And how do we get the latent representation? By passing an input to the encoder, and the encoder gives us the compressed version. Once we get the latent representation, this latent representation is passed as an input to the decoder for reconstruction. So, this is what is the latent representation. Now, whatever the limitations that we are seeing in autoencoders, all those limitations are with respect to latent space only. So, what is the first limitation? The first limitation here is there is no guarantee that the latent representation has captured the meaningful factors. So, although it is a compressed version of the input, there is no guarantee that the latent representation has a meaningful factors. Now, even though if the reconstruction error is very less, we cannot assure that the latent representation has a meaningful one. What exactly mean by this? There is one more meaning for meaningful factors is maybe the latent representation will not be having an semantically meaningful features. What is the meaning of semantically meaningful? These latent representation, whatever the features that we have, there is no guarantee that it is understandable by the humans. So, this is the first problem, and the second, this latent space, there is no guarantee that it has a task relevant features. What is task relevant features? Suppose if you take an handwritten recognition, handwritten digit recognition, this latent space will not assure that there is a proper shape, then the thickness of the strokes, there is no guarantee with all of these. So, this is the first limitation, and the first limitation deals with the latent space. Now, the second limitation, what is the second limitation with respect to latent space is, now we have obtained this by passing an input to a decoder, and we have got a compressed compressed version. Now whatever is this compressed version, which we are calling it as latent space, those features cannot be used for specific tasks such as classification, prediction, or clustering or anomaly detection. It is used only for reconstruction, but because we have got these features, we will modify the autoencoder architecture and then use these features for classification, prediction or clustering. It is not possible. That is the second limitation. Although we cannot say it is not possible, but there is no guarantee that you get a very good classification result or prediction result. That is the reason that these latent space features cannot be used for the following tasks. The third limitation here is, once we get the latent space, from the latent space, when you are passing it to an decoder, latent features, when it is passed to a decoder, decoder is reconstructing the input back. Now the decoder, for decoder the input is latent, so which means a compressed one is passed as an input to a decoder. Therefore whatever is the reconstructed input that we are getting or reconstructed data that we are getting, that is an approximation of the input, but not the original features. So this is the third important limitation of autoencoder. And the fourth one is, if the latent space size, we have seen that if the latent space is m and the input is n, m can be less than n or m is greater than n. Now if m is less than n and if m is very much smaller comparing to n, so if n is having 100 features and if m is having 25 features, a lot has been compressed. When lot has been compressed, there is a high chances that the information is being lost. And with this compressed one, when you are reconstructing the input back, then the originality will be lost. So this is the first point here. I am sorry, this is the second point. When the size is very much small, then a lot of compression is taking place, which leads to information loss. Therefore there is a poor reconstruction quality. And the second, when m is very much larger than n, then what exactly is happening, and when there is no regularization, do you remember the loss function, the loss term is also having an regularization term. If m value is very large and if the regularization term is not being used, then it leads to overfitting problem. And whatever the reconstruction that we are getting, it is a trivial reconstruction. What do you mean by trivial reconstruction? There is no proper learning that has taken place. Whatever the input, it is a kind of a rote memorization, and it is producing the output. So the model is not able to learn how to reconstruct when m is very much larger than n. So all these are the limitations of autoencoders. And if you look into these limitations has arisen because of this latent space only or latent representation. Therefore variational autoencoders, which in short we call it as VAE, addresses these issues. And how it addresses these issues? By introducing the regularization on this latent space. If the latent space is causing all of these limitations, then VAE actually addresses this by taking care of that latent space. How it is taking care? By introducing the regularization on the latent space. And VAE achieves this by adding something called as a KL divergence regularization term to the loss function. Therefore VAE, whatever the loss function that we have, to that loss function we will be having a KL divergence regularization term that we will be exploring. So, after we have understood the limitations of autoencoders, let us start with the architecture of variational autoencoder. So, I request the learners here to focus, because this is little heavy topic, but it is easy to understand. Now, let's I will be breaking down this into many smaller steps, so that you will be able to understand better. So, now what is that we have with us? We have an data. From this diagram, what you are seeing, the data what we have is the CSV data, the data which is stored in the CSV file, which means it is a structured data that we have. So, we have n samples with us. The data set will have n samples. So, how do you represent the first sample? This is the first sample, this is the second sample, third sample, and so on up to n samples. That is what is being written here. If you look into this data set, this all of these samples, there are three different classes here. It is an iris data set. There are three different classes. One is Sotazo, then we have Virginica, and we have Versicolor also. We have three different classes. Let us assume those three different classes are C1, C2 and C3. Now, when you look into, is it not there are some data points which will be belonging to one class, there are some data points which belongs to another class. So, that is what is being written here. There are some points which belongs to C1, the class C1. There are some points which belongs to some data samples which belongs to an other C2 class. There are some points which belongs to C3 class. So, what we have understood so far, we have a data samples data set which is having n samples, and if you take a data set, the data set is having an class, and all of these belongs to some points belongs to one class, some other set of points belongs to another class, then other set of points belongs to an class 3. Don't be in the confusion. Just because here we have taken a class, it means we are dealing with the supervised learning. No, even though there is a class, nowhere we will be using this. I am just trying to tell you that there are some points which belongs to one category. So, that category here is C1. There are other set of points which belongs to another category, other set of points belongs to another one. So, or rather you can understand, all of these points are together, all these points are together. So, you can understand even in this way. So, although we are using just for example sake, I am using the classes here, but VAE is one of the example of unsupervised one. Okay. Now, if you look into, so far what we have discussed, there are some points which belongs to one class. Now, when you look into all of these points, now the points which are of the same here are all similar. If you look into, the values of all these samples are similar, the values of all these samples are similar, here the values are similar. So, the points belonging to a same class will be all similar, and if you look into another, if you look into this, all these points are similar. If you look, so what point I am trying to explain here is, the points belonging to a same class are all similar, the points belonging to a different class are far away from each other. So, what does it mean? Each class here follow its own data distribution. What is the meaning of this? When we take the mean of this, you will have one value. When you take the mean of this, you will have one value. When you take the mean of this, you will have a different value here. So, the distribution of these points and the distribution of these points are different. That is what is being written here. So, what does it mean? What is the probability of this, how do you read this? The probability distribution of the, feature value x given in class C1 or belonging to a class C1. Similar way, the probability of x given a class C2, the probability of x given a class C3. Okay. So, in short, what we have understood, there is a data set which is having n samples, and these data sets, there are so many samples, and there are few samples belongs to one class, few samples belongs to a second class, and few points belongs to another class. Every point, every set of samples which are belonging to one particular class will follow its own data distribution. Now, the most important is, do we know what is the distribution of this? All we have is just the data, right? So, we do not know what is a true data distribution. So, we do not know this, and most important, we do not know what is its functional form also. What is the true functional form? Whether the data is coming from a Gaussian distribution, or whether it is a Bernoulli, whether it is a binomial, whether it is a Poisson. We do not even know to which distribution our data belongs to. We doesn't even know that basic also. If we doesn't know any of this, obviously we doesn't know its parameters also. What do you mean by parameters? When you say it is a Gaussian distribution, then we will be learning mu and variance or standard deviation. When it is a Bernoulli, we will be going for its probability. So, when we doesn't know what is its functional form, we doesn't know its parameters also. If that is the case, what is that we know? All we know is just the samples. We have only the data set. Okay. So, what is our first aim here? The primary objective, VAE is a generative model. So, the primary goal of any generative model is to first learn that unknown data distribution. What do you mean by unknown data distribution? The unknown data distribution is, first we should know to which functional form it is taking and its parameter. Suppose if you assume that the data is from a Gaussian, then the goal of any generative model is to learn this data distribution, that is the mu and variance. First step is it has to learn that underlying unknown data distribution, and the second, once it learns that data distribution, the second objective of any generative model is to generate a new sample. So, what is that new sample? The new sample is x new, and what is our aim? It has to look as similar as training data. So, whatever is the new sample that we are going to generate, it should match to an training data. So, from this particular slide, two important points that you need to take. The first is, all what we have is just the data. We doesn't know its functional form. What is the data's functional form? To which distribution it belongs to? What are its parameters? Nothing we know. All we have is just the data. So, first step of any generative model is it has to learn that unknown data distribution, and the second, once it learns the unknown data distribution, it has to generate a new sample. So, this is what you need to take from this particular slide. Now, there are two distributions that we have. So, all what we have is just the data. So, that data belongs to some distribution. So, which is that distribution we have to learn, but we definitely know that the data belongs to some distribution. So, the out of two distributions, the first distribution is a data space distribution, which we denote it as a P data P of x. So, P data of x, why exactly it what exactly it is? It is the distribution of our input data. And now, we know that from the input, when it is passed to some model, we are going to get the latent space or latent representation. From the input, you are getting the latent. That means, which is nothing but this is also a kind of compressed data only. That that data also will belong to some distribution. That distribution we call it as a P of Z. So, here we are denoting two distributions, P of X, which we call it as an data distribution, given input to data distribution, and from input we are going to get the latent space, which is latent space is also having a data. So, that data's distribution is P of Z. Now, these two terms you understand. Next, since X and Z live in two different spaces. What do you mean by X and Z live in two different spaces here? Now, when you look into the dimensionality of X and dimensionality of Z, the structure of X and structure of Z are two different. We require a probabilistic mapping to connect this X and Z. Since X and Z are living in two different spaces, we require a probabilistic mapping. What is that? The first probabilistic mapping. The first probabilistic mapping is, you see, we need a connection between X and Z. What is that connection? What is the, how do you read this? You will read this, the probability distribution of the latent space Z given the input data X. So, that is how you will read this. So, the very first mapping that we are doing is what is the probability distribution of Z? What you have is just the X, given X. So, this term we call it as a posterior distribution. We call it as a posterior distribution, and it is an encoder. And the second probabilistic mapping is likelihood distribution. What is likelihood? Now, you have Z. What is the probability that we will get the reconstruction X given this Z? So, this is the likelihood distribution. What is the probability of reconstruction data X given the latent space Z? So, one is mapping, so what exactly? One is a mapping from input to latent, and the second distribution is a mapping from latent space back to data space. So, these two are the probabilistic mapping. Now, the first here is you have to learn that latent space, that is the primary objective here. So, the primary objective here is to infer the posterior distribution. How is that? What is a posterior distribution? It is a P of Z given X. So, how is that? You will be writing using a Bayesian Bayes rule. You can write P of Z given X as P of X given Z, P of Z divided by P of X. This is a standard Bayes rule. So, from this we have defined P of Z given X. Now, let us try to understand each of these terms. Now, what is this? This is P of Z is nothing but, Z is nothing but a latent space. Now, if you go back and then recall from our previous sessions also, if you have 100 features and when you pass it to an encoder, after you compress, you will, if you define the space as 25, then it means you have now 25 features. Here you have 25 features here. So, which means the Z, the latent space what we are getting is not a single number. So, in VAE the latent space is not a single number, but it is a vector. Why it is a vector? So, from 100 when you pass it to encoder, when you get a 25, it is 25 values that we have Z1, Z2 and so on up to Z25. So, in general you will be having ZD features you have. So, from this what you are understanding, it is not a single number, but it is a vector. Z is a vector. Now, do you all agree to this? The primary objective here is to learn the latent space, but here we do not know what is the structure of the latent space. What does it mean? All what we have is just the data. We have still not started learning anything. So, which means the primary objective here is to learn the latent space. If you have to learn this latent space, we do not even know what is the structure of this latent space. Therefore, we make the first assumption here. What is that assumption? From input, when you pass it to an encoder, you get the latent space. The probability distribution of this latent space is what we doesn't know. So, therefore, the assumption what we make is P of z is a Gaussian distribution, or we will this P of z is unknown, and that we are going to have an assumption. And what is that assumption? P of z is from a standard normal distribution, which is nothing but a Gaussian standard normal distribution with the mean 0, variance 1. So, this is the first assumption we are doing, because from input, when it is passed to an encoder, we get a z. We doesn't know what is the probability distribution of this z. Therefore, we make an assumption that this belongs to a normal distribution which is having a mean 0, variance 1. So, this is what is the assumption that we are doing it. Now, because of this assumption, what is the assumption? That P of z is a normal distribution. Therefore, because of this, is it not you are enforcing one structure onto a latent space? So, it is an latent space is well structured, and it is having an continuous values. Now, this is what we have understood with respect to P of z. P of z, we are assuming that the distribution of this is a normal distribution. Now, we need to understand this, because ultimate aim is to calculate this. In order to calculate, we should know each of these terms. Now, how do you write P of x? From a standard definition, P of x is an integral over P of x given z, P of z dz. So, this is the definition of P of x. Now, computing P of x is very hard. Now, we need to understand why computing P of x is hard. Let us understand this, but we will understand this in a while. We will come back to this point. Now, we have understood that P of x, for some reason, still that reason is unknown to us, but P of x calculation is very hard. Now, when P of x calculation is very hard, which means denominator is very difficult part. When denominator is very difficult, when it is not possible to compute, then can you calculate now P of z given x? When this is not possible, can you calculate this directly? Answer is no. Therefore, we do not compute P of z given x directly, but instead we choose something called as Q of z given x. What is that? We intentionally choose this. What is this? This is a variational approximation to this value only. Instead of directly computing a P of z given x, we compute it using a variational approximation by choosing a Q of z given x. So, how do you write this? P of z given x is what we need to calculate, but we are approximating it using this term. Now, we are doing a second assumption. What is the second assumption? This Q of z given x is a Gaussian distribution. To be Gaussian is an assumption that we are doing. Now, whenever you say a Gaussian, the parameters of a Gaussian are mu and then variance. So, these are the parameters. Now, the parameters mu of x and variance of this Q of z given x, this you have to learn. And who is helping us to learn this? It is an encoder network which will learn this. So, two terms I have introduced. One, the primary aim here is to learn P of z given x. P of z given x is written in this particular form. Now, we have understood that the probability distribution of P of z is a normal distribution. Then, we have also seen that calculating P of x is very hard. The reason is still we have not explored, but we know that P of x calculation is very hard. Because P of x calculation is very hard, this P of z given x cannot be computed directly. If you cannot compute this directly, then how are you computing it? You are computing it by considering the approximation. So, q of z given x. Since p term we have already used, we are using a term q. Now, here the second assumption, the first assumption is to this term, second assumption is this is Gaussian. So, why? Ultimate aim is to learn this underlying probability distribution. So, therefore, the assumption that you will be doing is it is an Gaussian distribution. And what are the parameters for the Gaussian distribution? It is a mu, and then the variance are the Gaussian are the parameters of Gaussian. Now, who has to learn this? It is an encoder network who will learn these two distribution. Now, there is one important question. That question is, why did we assume q of z given x as Gaussian only? Why did we assume this? Now, for this the answer is input which is x, when it is passed to an encoder, encoder is learning, encoder has to learn these parameters, right? Now, the question is, why did you choose Gaussian so that encoder is learning these parameters? Why do you think? Can you recall the concept? From input, when you pass it to an encoder, you will get a latent space, correct? So, what is this latent space? If you denote it as a z, the latent space is denoted it as a z, we are denoting it as z. We have done one prior assumption here. What is this assumption? The probability distribution of this z is a normal distribution who is having a, which is having a mean 0, variance 1. You have made this assumption because you have made the assumption that z is the probability distribution of z is standard, that is Gaussian or a normal distribution. When from input, when you get that z, obviously input has to be the Gaussian only. So, here the prior distribution P of z serves as a reference distribution for q of z given x. Because P of z is assumed to be a normal distribution, the reference we are taking that q of z given x is also a Gaussian. Now, again there is one more question. What is that question? Who will ensure this, that because that is Gaussian, encoder also should follow the Gaussian. Who has to ensure this? We have an KL divergence. KL divergence is a term which will ensure that something is already a normal distribution. Now, this q of z given x also should match to that normal distribution. That is taken care by KL divergence. In the next session, we will be seeing the decoder part of the VAE. We will also see the loss function of VAE, and we will understand VAE working, the working mechanism. We will see one entire forward pass by considering one numerical example. So, in this particular session, we have seen only the encoder part of an VAE. In the upcoming session, we will continue with this VAE. Thank you.